Hello, Tensor friends. Excuse me. I was working on something today that involved a covariant derivative, and I started thinking about who did what, when, where, why. And it led to and some interesting the reading. I looked all this up on the internet. I don't have access to university libraries, so I just had to do it that way. But anyway, I found out some interesting things. So I just entitled this from this, which is the theoremum egregium from Gauss to Einstein's field equations. How did we get from here to here, right? Now, a differential geometry, the thinking of it goes back all the way to the ancient Greeks. We don't want to go that far because it's a lot of information and we don't want to take that much time. So let's start with a biggie. Carl Friedrich Gauss. So in 1928, Gauss published an essay called The General Disquisitions About Curved Surfaces. I had to look this word up. A disquisition is an essay, a long essay about one subject. That's what it means. I don't think anyone uses it anymore. Anyway, this was his first step in non Euclidean geometry in defining intrinsic curvature, right? In his essay, he wrote something that looked like this. This is very familiar looking, right? So later on, we would know that this is an example of a Riemannian, the metric. I'm not sure what this part is, but that's what it became. Okay, then his student Bernard Riemann in 1954 presented his on the hypothesis underlying geometry. In this, he wrote, I have in the first place, therefore, set myself the task of constructing the notion of a multiply extended magnitude out of general notions of magnitude. It will follow from this that a multiply extended magnitude is capable of different measure relations, and consequently that space is only a particular case of a triply extended magnitude. Now, today, in modern words, we call multiply extended magnitudes as manifolds. And the measure relations he referred to, we now call the metric. Okay? So this was the birth of Riemannian geometry. Uh, and unfortunately, the poor fellow didn't live very long. Who knows what he would have become? He really was an amazing guy. You should take time and read about him. Then Elwin Bruno Christoffel in 1869. Okay, so we started in 1828. Is that right? 1828. We went to 1854. Now we're up to 1869. He published this paper on the transformation of homogeneous differential expressions of the second degree. He introduced the fundamental technique later called covariant differentiation. So I did not know he was the first one to come up with that. He didn't call it that, but that's what it was. And used to define the Riemann-Christoffel tensor, which, as we know now, is the tensor that defines curvature on a manifold. In the same paper, he introduced the Christoffel, the symbols of the first kind and second kind, which express the components of what would be called the Levi-Civita connection with respect to a system of the coordinates. Okay, so it's all coming together. Then here come the big one. Ricci and his student Levi-Civita, around the turn of the century, published Absolute Differential Calculus, where they took all that prior work and put it all together in a meaningful way to produce what we now call tensor, the calculus. Okay? So Albert Einstein is next. And all of the stuff that these guys had worked on, right? Everybody works on something that's built from something before them. So all the pieces were there. Riemannian geometry was there to describe a new field of physics. And in 1915, Albert Einstein had the brain power, the absolute insight to put that into application of the general theory of relativity. So it really amazes the crap out of me how all this stuff came together at the end by Albert Einstein. Now, he didn't do it by himself, right? He said so himself. He had lots of help here. His the friend, Marcel Grossman, was a professor and knew about differential geometry, so he helped him with that part of it. But I just find that fascinating. I would encourage anyone to read the history of this stuff. All right, see you later.